The combustion chamber, or combustor, must contain the burning mixture of air, which is being passed from the compressor, and fuel, from the fuel spray nozzles, in order to generate the maximum heat release at a substantially constant pressure, so that the turbine receives a uniformly expanded, heated, and accelerated stream of gas. This is not an easy task, but advancements are constantly being made in combustion chamber design to enable more efficient use of fuel with less and less pollution of the atmosphere. Efficient combustion has been made increasingly more important because of the rise in the cost of the fuel, and also the increasing awareness of the aviation industry and the general public of the dangers of atmospheric pollution from the exhaust smoke. There is a limit to the maximum temperature of the gas exiting from the combustion chamber. This is imposed by the materials from which the nozzle guide vanes and the turbine blades are manufactured. The slightest excursion above that temperature limit will mean distortion of the turbine blades and the possible disintegration of the turbine, with probably catastrophic results. Modern turbine and nozzle guide vane materials will allow a gas temperature not exceeding 1700 degrees Celsius when it exits the combustion chamber. Considering that the air which leaves the high-pressure compressor may already have been heated to around 550 degrees Celsius during its compression, we can add sufficient fuel to raise the temperature of the gas exiting the combustion chamber by a further 1150 degrees Celsius, before we exceed the limit temperature of 1700 degrees Celsius. It must also be remembered that the combustion chamber has to be capable of maintaining stable and efficient combustion over a wide range of engine operating conditions. Of course, 1700 degrees Celsius would be the temperature of the gas exiting the chamber with full power selected. Lower power settings would require lower fuel flows, and consequently would generate lower gas temperatures. You'll see from this graph that the air enters the combustion chamber at a slightly slower rate than which it enters the intake of the engine. Speeds of around 500 feet per second are not unusual. The flame rate of kerosene, that is, the speed at which the leading edge of a flame would travel through kerosene vapour, is approximately 30 feet per second. If burning kerosene was exposed to an airstream which was travelling at 500 feet per second, it would be extinguished immediately. So, something must be done to slow down the speed of the airflow after it leaves the compressor, and before it reaches the combustion chamber. Otherwise the flame would not be sustainable. At this position on the graph we see how this reduction in the velocity of the air is achieved. The air is slowed down, and, an added bonus, its pressure is increased after it leaves the compressor by passing it through a divergent duct immediately before it enters the combustion chamber. In fact, the pressure attained at this point, at the end of this divergent duct, just before the air goes into the combustion chamber, is the highest in the whole of the engine. The reduction in velocity is still not enough, however. Further decreases must be achieved if the flame is not to blow out. The air is divided after it exits the high-pressure compressor into primary, secondary, and tertiary airflows. We'll now examine each of them. This diagram shows how the air entering the flame tube passes through the snout before being divided to go through the perforated flare and the swirl vanes and into the primary zone. The primary zone is a region of lower velocity recirculation, positioned immediately downstream of the fuel spray nozzle, It's within this zone that stable combustion is achieved. The primary air is approximately 20% of the total airflow coming from the high-pressure compressor and into the combustion chamber. This is the air which is mixed, in a ratio of approximately 15:1 by weight, with the fuel and burnt. By being passed through the flare and the swirl vanes, the velocity of the primary air is reduced, which must happen if the flame is not to be extinguished, and the shape and position of the flare and swirl vanes also starts the air recirculating within the region. The remaining 80% of the output of the high-pressure compressor, air which has not been directed through the snout, goes into the space between the flame tube and the air casing. Some of this remaining air, approximately another 20% of the output of the high-pressure compressor, is allowed into the flame tube through secondary air holes. This air is called secondary air, and it reacts with the primary air, which is flowing through the swirl vanes to form a toroidal vortex. The toroidal vortex stabilizes and anchors the flame and prevents it being moved through the flame tube away from the fuel nozzle area. The temperature of the gases at the center of the primary zone reaches about 2000 degrees Celsius. This is far too hot for the materials of the nozzle guide vanes and turbine blades, so a further drop in temperature is required before the gases can be allowed to exit the combustion chamber. The remaining 60% of the total air coming out of the high-pressure compressor is progressively introduced into the flame tube through corrugated joints and dilution air holes in the flame tube. This air is called tertiary air. Tertiary air is used to cool both the air casing and the gas exiting the chamber. The type of combustion chamber which we have used to illustrate the interaction of the flame and the cooling air is representative of those which would have been used in an early multiple combustion chamber system. Different methods of keeping the combustion chambers from overheating are used. Some flame tubes have ceramic-coated tiles fixed to a skin on their interior walls. Cooling air passes through the holes in the skin and flows between the skin and the tile, which has a ridged surface. The ridged surface improves the heat transfer between the tile and the air. The air finally enters the flame tube at the front and rear of the tile and forms an insulating film for the tile as it flows over it. Other engine designs use a different method of cooling the air casing, which is called transpiration cooling, where a film of air flows between laminations, which form the flame tube wall, and then exits the laminations to form an insulating film of air within the flame tube. This picture illustrates several other features of the type of combustion chamber which would be used in a multiple combustion chamber system. Although the engine would probably start quite readily with only one igniter operating, most gas turbine engines have two igniters. However, because there are only two igniters, another means of passing the starting flame between the combustion chambers in this type of system has to be found. This is called the interconnector. Immediately after light-up, the flame in the combustion chambers which have the igniters causes an increase in the pressure within those chambers. The pressure differential between a chamber which has a flame in it and those adjoining it which have no flames drives the burning gases through the interconnector pipework. When the burning gases come into contact with any unlit mixture in the adjacent combustion chamber, they ignite that mixture. This process is continued around the engine until the contents of all of the chambers is burning, whereupon the pressures within them are equalized and the flow through the interconnectors ceases. The sealing ring at the turbine end of the combustion chamber allows for elongation of the chamber due to expansion. The chamber is fixed at the compressor end by being bolted onto it, and it cannot expand in that direction. The sealing ring allows the chamber to expand into the nozzle box, which is the portion of the engine immediately preceding the nozzle guide vanes, while maintaining a gas-tight seal between the chamber and the atmosphere. The straight-through flow multiple combustion chamber system was developed from Sir Frank Whittle's original design, which was supplied with air by a centrifugal compressor. The straight-through combustion chamber system was later used on some earlier types of axial flow engines, and is still in use on centrifugal compressor engines such as the Rolls-Royce Dart. The multiple combustion chamber system consisted of a number of the individual combustion chambers, which are shown here. Each combustion chamber consists of a flame tube, which has its own air casing. The combustion chambers are disposed around the engine just to the rear of the compressor section. This picture shows a multiple combustion chamber system similar to that used in the Rolls-Royce Avon, which was a powerful, for its time, axial flow compressor engine used on many different types of aircraft, both military and commercial, fighter and transport, for a considerable number of years. Shown here are the snout, the primary air scoop, the interconnectors, and the drain tubes. The drain tubes allow the drainage of excess fuel from the combustion chambers in the unlikely event of the engine failing to start, an event which is more commonly called a wet start. A wet start happens when the mixture of air and fuel in the combustion chamber fails to ignite during a start. A considerable amount of fuel will have been fed into the combustion chamber during the attempt to start. If that fuel is not removed before the next attempt to start, and if that attempt is successful, the result will be a combination of excessively high gas temperatures in the turbine region and torching, which is the name for a very long, very hot and very dangerous jet of flame issuing from the rear of the engine. Two means of getting rid of the fuel are open to us. First, the fuel drain system, and second, a method of evaporating the remaining traces of fuel from the combustion chambers, the turbine, and the jet pipe. The fuel drain system utilizes the drain tubes which connect the lowest part of each chamber with the next chamber below it. Fuel remaining after a wet start will attempt to find its own level by flowing from the top of the engine to the bottom chamber. Once in the bottom chamber, the excess fuel exits the engine. Any remaining traces of fuel within the engine must be evaporated. To this end, the engine must be motored over on what is termed a blowout cycle. During a blowout cycle, the engine is turned over by using the starter motor. It's rotated for the time normally allocated to a full start cycle, but with the high-pressure fuel cock shut and the ignition system deselected. Air from the compressor will flow through the combustion chambers, the turbine, and the exhaust system, and assist in the evaporation of any fuel still remaining within. The tubo-annular combustion chamber system, shown here, is sometimes also called the cannular or can-annular system. The tubo-annular combustion chamber system differs from the multiple combustion chamber system insofar as it does not have individual air casings for each of the flame tubes. A number of flame tubes are fitted within an inner and an outer air casing, which makes this system a more compact unit. Notice the position of the igniter plug. This illustration is of a typical example of an annular combustion chamber system. It has only one flame tube, which is contained by an inner and outer air casing. The annular system has several advantages over the multiple combustion chamber system and the tubo-annular system from which it was developed. They are: for the same power output, the length of the annular chamber is only 75% that of a tubo-annular system of the same diameter. There are no flame propagation problems. Compared to a tubo-annular system, the air casing area is less. Consequently, less cooling air is required. The combustion efficiency is raised to the point where unburnt fuel is virtually eliminated, allowing the oxidization of carbon monoxide to non-toxic carbon dioxide. There is a much better pressure distribution of the gases impinging on the turbine, so it has a more even load placed upon it. We stated at the beginning of this lesson that we had to obtain the maximum heat release from burning the mixture of fuel and air in the combustion chambers. To do this, we must use the chemically correct air-fuel ratio of 15:1. Whereas in the piston engine the use of the chemically correct air-fuel ratio of 15:1 would cause detonation and dissociation to occur, in the gas turbine engine it poses no such problem, because there are no peaks of pressure to assist in their generation. The fuel and air are therefore mixed and burnt in the primary zone of the combustion chamber in the ratio of approximately 15 units of air to 1 unit of fuel by weight. The addition of secondary and tertiary air will, however, dilute the mixture, to the extent that the overall ratio may vary from between 45:1 to as weak as 130:1. In the introduction lesson, we stated that combustion theoretically occurs at a constant pressure. In fact, as is shown here, a small loss in pressure does in reality occur, as the gas passes from the compressor end of the combustion chamber to the turbine end. This loss of pressure is caused by having to provide adequate turbulence and mixing. Losses vary from 3 to 8% of the pressure at the entrance to the combustion chamber. During normal engine running conditions, combustion is self-supporting. The ignition system is actually switched off as soon as the engine has attained self-sustaining speed. Self-sustaining speed is the speed at which, after start, the engine can accelerate without the assistance of the starter motor. There may, however, be certain engine operating conditions which do require the use of the ignition system. For instance, just such a condition would occur following a flame-out, which is extinction of the flame due to various unusual occurrences, such as the ingestion of large quantities of water thrown up from the nose wheels into the engine intakes during takeoff from a heavily contaminated runway. Combustion stability means smooth burning of the mixture, coupled with the ability to remain alight over a large range of air-fuel ratios and air-mass flows. This graph shows the limits of those air-fuel ratios and air-mass flows within which combustion will remain stable. The graph shows that combustion stability will occur only between a narrower and narrower range of air-fuel ratios as the air-mass flow through the engine increases. And beyond a certain level of air-mass flow, the flame is extinguished. Outside the ignition loop, which lies within the stable region, it is more difficult to start combustion than it is to sustain it once it has started. Restarting the engine in the air while it's windmilling is called a relight. A consequence of this is that, should the engine flame out at high speed or high altitude, it may be necessary to slow down and/or descend before the engine can be successfully relit. This graph illustrates a relight envelope for an imaginary engine, showing the flight conditions under which it would be guaranteed to relight if it was fully serviceable. The airflow through the engine will cause it to rotate or windmill, so the compressor is supplying sufficient air to support combustion. All that is then required is the opening of the high-pressure fuel cock to deliver a fuel supply, and operation of the ignition system to add the final ingredient, a spark. Operation of the ignition system to supply the spark is achieved by selection of the relight switch. The electrical power to the relight ignition circuit functions independently from that which feeds the normal start circuit. Combustion efficiency is the efficiency with which the combustor assembly extracts the potential heat actually contained in the fuel. This graph shows the combustion efficiency of a modern gas turbine engine across the range of air-fuel ratios which occur during normal operating conditions. Modern gas turbine engines have a very efficient combustion cycle. At high power operating conditions, combustion efficiencies as great as 99% are achievable. And at idle, the systems will still give as much as 95%. The very high combustion efficiency attained in modern gas turbine engines is due in no small part to the fuel spray nozzles which are used in them. These nozzles have the task of atomizing or vaporizing the fuel to ensure that it is completely burnt. This is no easy undertaking, considering the velocity of the airstream from the compressor and the small distance available within the chamber for combustion to occur. Other difficulties occur as a result of the relatively low pressures attainable by the engine-driven high-pressure fuel pump at engine start. The pumps can be of the plunger type or the gear type. The pumps are fitted to the high-speed gearbox, which is driven by the high-pressure compressor shaft. The pumps are only rotating at a minimal speed during initial engine start, and are incapable at that speed of providing the high pressures, 1,500 to 2,000 pounds per square inch, required to give a good spray pattern. At engine start, when there is low engine RPM and low fuel pressure, the fuel spray pattern forms what is known as a bubble. This spray pattern is unable to atomize the fuel jet sufficiently for ignition to occur. As the engine accelerates during the start sequence, the pump rotates faster and builds up more pressure until the spray pattern forms a tulip shape. Atomization is still not sufficient to support combustion. Eventually the pump produces sufficient pressure to shorten the tulip until it touches the orifice. Only now is the fuel jet atomized sufficiently to ensure rapid burning. We've demonstrated then that a small orifice of fixed size will provide a finely atomized spray at high fuel pressures. However, when higher volume fuel flows are needed through larger bore nozzles, the pressures required from the pumps to provide that finely atomized spray become unattainable. Thus, for that type of situation, other methods must be found to sufficiently atomize the fuel at engine start when fuel pressures are low. The air spray system uses a high-velocity airstream to break up the flow of fuel. It requires only relatively low fuel pressures, and can therefore operate using the gear-type pump, which is much lighter than the more sophisticated plunger-type pump. The duplex system, and shown here the duple spray nozzle, effectively use an orifice of variable size. At low fuel pressures, a pressurizing valve closes off the main fuel feed to the nozzle, the only supply coming from the primary fuel line. The primary fuel line feeds the primary orifice, a relatively small hole, which is capable of providing a finely atomized spray at lower fuel pressures. When the engine accelerates during start, fuel pressure builds until the pressurizing valve starts to open. This allows fuel to flow through the main orifice, where it will supplement the spray of fuel from the primary orifice. In the vaporizing tube method, illustrated here, the fuel is sprayed from feed tubes into vaporizing tubes, which are positioned inside the flame tube. Primary air is fed into the flame tube through the fuel feed tube opening, and also through holes in the flame tube entry section. The fuel is turned through 180 degrees, and as the vaporizing tubes are heated by combustion, the fuel is vaporized before passing into the flame tube. This concludes the lesson on combustion chambers.